All right, so welcome back again, everyone. We just finished up going over weeks 1 through 7 discussion posts on uh, the underground mining course, and now we're going to do the same exact thing with the surface mining class discussion posts. Discussion posts for it. So here we go. Once again, introductions. Um, everybody did those, and almost everyone is in both courses, so it's basically just a repeat. That's fine, but introducing yourself to everybody got everyone 5 bonus points. So let's move on into week 2 and go from there. So the discussion post for week 2 was last week we covered a high overview of surface mining methods. Okay. And you saw that each method has, advantages and limitations, right? Depending on the situation. This is basically just a rewording of the underground discussion prompt to apply to surface mine techniques. So in your post, you need to identify 3 key factors that should be considered when selecting a surface method and explaining why they matter in practice. Okay. So 3 that I can think of just off the top of my head, and that a lot of students suggested, okay, was that number 1 is the commodity again, right? So the commodity a lot of times dictates, the layout and the type of reserve, right? So for example, a thin gold vein that's in some quartz that's part of an igneous intrusion into whatever granite or something like that, some kind of hard rock. Yeah, you're going to be looking at surface methods that are probably open pit in nature, right? So you'll be removing overburden, and of course you'll have this sort of high concentration of material in the middle. But on the other hand, other hard rock situations where you have, a large ore body, okay, are traditionally also mined with, open pit methods. But the commodity is important. So for coal, generally speaking, you'll be considering mountaintop removal, contour mining, strip mining, that sort of thing, right? Um, Another, feature is going to be the geometry of the reserve once again, right? That was the same thing that we talked about in the underground portion, but that matters again, right? Like if you have a big, vast territory, so think of like Eastern Ohio, for example, right? Large open areas. You can strip mine those with maybe drag lines or large shovel, truck shovel fleets, that sort of thing. And so the area matters, right? And so what else? A third option, third factor might be, exactly how many seams or you have. So in coal, for example, if, on the property there's 6, 7 seams or so, then yeah, you're going to want to probably consider a mountaintop removal type situation where you're accessing those seams on the way down. However, a lot of those areas are, limited to where, we've mined a lot of those in the past, right? And there's not as much, available anymore. And a lot of times what you're going to see is, contour mining, particularly on the steepest slopes, like in this area, that, southern West Virginia, central Appalachia, that sort of thing, right? And so why these matter in practice is, if you select a wrong method, it's gonna cost you, right? So methods in the end are dictated based on the economics, right? You're going to do whatever you can based on which practice is going to, provide you the most revenue, right? So that's pretty much, what I was going for with that particular discussion post. Moving on to week 3, um, we talked about blasting and surface mining, and then including drilling geometry, explosives, loading, powder factor, that sort of thing. And what I wanted you to consider with that was, why do you think the powder factor is often called the economics of blasting? Everyone, I think, knew what this was, discussed it pretty thoroughly, and it's the economics of blasting because it dictates how much powder you're going to put in the hole, right? And powder costs money. The explosive agent that you're using, be it AMFO, emulsion, whatever, is the one of the primary costs in removing the overburden, right? Which then goes into the stripping ratio calculation, and which determines the economical mining limits, right? So that's a big factor in that cost. And then the second was part B, I guess, was what is one potential hazard of poor blast design, and how does good design prevent it? There's a number of options here. Some students went with, for example, just pointing out that if you used a blast design that was designed to, make a corner, and you're not making a corner, then that wouldn't work. And of course, that's a good answer. If you're obviously doing something completely wrong, that's one thing. Some people talked about putting in too much explosives, causing fly rock, that sort of thing. Yeah, it is a hazard of poor blast design for sure. We should be minimizing fly rock, especially when we're, blasting near structures and that sort of thing. Another would be just a rough, high wall based on maybe over blasting in the last row, whether you pre-split it or not, which, most high walls are going to be pre-split. That is, you shoot the back shot first, you split the high wall where you want it, and then you blast the rest of the material after that on a delay. That is, most common. But whether you do it or not, if you have issues with that break, right, you're going to have potential issues with, fragmented rocks as part of the high wall and that sort of thing. That's one issue I would, consider when I'm thinking about, the potential hazards of your blast design. Moving on to week 5, explain in your own words why the stripping ratio is such an important factor in surface mining. Give an example, real or hypothetical, of how changing either overburden thickness, coal seam thickness, or coal price could affect whether a mining project is considered feasible. Stripping ratio is important because, once again, it determines the economical limits of your surface mining operation, right? That if you exceed those limits, if you remove more overburden than that, then you start losing money, right? That it's costing you more money to remove the material than it is to sell the product. And so that's why it's so important. You're not going to mine that if it's not profitable for you, and it provides the limits. So an example, we can talk about any of these. Like if you move from one area of the mine to another, and your overburden increases significantly, right? Then obviously your stripping ratio is going to increase, right? You're going to be removing more overburden, right, per yard or ton of material that you're mining. So it's going to go up, and it's going to impact the economical limits of mining, right? If you're in a coal mine, for example, a contour strip or something like that, it's going to affect that that maximum allowable bench width. And that can, do a number of things, right? It could decrease your bench width to where you can't, highwall mine anymore, right? And actually get to a point where it, may not even be economical to mine at all. The same thing can happen with the coal thickness, right? If it decreases significantly enough, then that impacts your stripping ratio again, increasing it and making the project less feasible, right? Thicker coal is obviously always better. And then coal price, you know, that's kind of given. If you went with that one, then you could just theoretically think that, in 20 years' time, the coal price might fall in half, and therefore, your stripping ratio, increases and basically probably doubles, and that sort of thing. And your economical limits of mining, decrease again, right? So all these things, the overburden, the thickness of the coal, and the sale price, all are, impact the stripping ratio, the maximum allowable stripping ratio, maximum allowable bench width, all those things, right? So moving on to week 6. We talked about highwall mining design. It requires engineers to set values for key parameters such as web pillar width, barrier pillar size and spacing, mining height or penetration length, mining depth or penetration length, mining height, and extraction sequence. Well, extraction sequence is kind of given. You're just going to mine the holes all in a row, right? You're going to start at the beginning and work your way out as you go. But each of these choices affects recovery, stability, equipment performance, project feasibility, and I asked for people to select one parameter from the list. Some students chose the web pillar. Some of them chose, barrier pillar and spacing. There was a few, others that chose different parameters, and explain how you would determine what value you use in a real world project. For the web pillar width and the barrier pillar sizing, the easiest way for the vast majority of projects is going to be using ARMPS, the analysis of retreat mining pillar stability, highwall miner. ARMPS HWM is going to be the most effective method to design your pillar sizing for. Sorry, I got a phone call and I have no idea where we stopped at, but it's too late. We're in too deep. We're not going back and starting from the beginning. And instead, we're just going to say, long story short, for week 6, anything to do with the pillar width, barrier sizing or width, the spacing of those, that sort of thing, is all going to basically be, dictated by, the stability factor that you get when you do your pillar design, right? Mining depth or penetration length, to determine that in a real world project, you're basically going to use your geometry, right? You're going to know this, the layout of the reserves. You're going to know what that looks like. You're going to know the property boundaries and all that sort of thing. And so you'll be able to choose that penetration length based on how much, coal is there. Keeping in mind that to be careful, I do know of a place. It was before I worked there, but it was a place that I worked at where they did lose a miner because they actually punched out on the other side and realized it, and were actually mining out into the backfill, right, of the strip on the other side of the mountain, right. So they mined through and got over into the backfill and actually lost the miner over in there, and it ended up being abandoned. They left it because it would have cost too much to go and get it. So do keep that in mind that, when you're thinking about the penetration length, don't punch out, please. That's a little bit too risky. Not necessarily for people so much. Usually there's no one over there or that sort of thing, but you're gonna lose some equipment, right? And then you're gonna have to come up with potentially a recovery plan to go in there and get your conveyance cars, whatever for the ag car system. It's cars. I don't know what they call it for, the other system, but you're going to have to go get those, right? So be careful with that. Entry height is going to be dictated by the coal seam itself or the equipment limitations, right? Typically in Appalachia, for the most part, if you have a highwall miner, you're going to size it sort of based on the majority of your reserves. And when things are, coal seams are thinner than that, you'll probably be taking some extra rock, get some out of seam dilution. And if they're considerably thicker than that, one technique you can use is to do multiple lifts, right? You can mine the top part and then come back and mine the second, and then you have an opening that's twice as high as it originally was. That sort of thing. You can do that. But generally speaking, your entry height is going to be based on the thickness of the coal or the equipment sizing, and then extraction sequence. Really, they're really that it's not like a cut sequence underground where you're like taking this cut and then you move over and you take this cut and you come back and you make this whatever. It's not like that. It's not exactly what I was thinking with this. And it's the extraction sequence in the terminology, the framework of highwall mining would be where do you put your longest holes? And generally speaking, that's as soon as you possibly can, right? As soon as you can, you want to get the longest hole depth possible. That way you're in the coal as long as possible, as early as possible, right? So it's all about putting tons on the ground as quickly as you feasibly can, right? Because we don't sell tons underground. We sell them sitting on the ground, sitting in the train, sitting at the port. That's where they're sold at. So you want to get that to that location as efficiently as you can. Identify the main factors that would influence your design decision. So the main factors influencing pillar design is going to be primarily the depth, right? The depth of cover is going to dictate that. In single seam sort of situations, or even multiple seam situations where it's only highwall mining that's going on, right? Where you're kind of, basically stacking your pillars the best that you can and that sort of thing. Uh, Not necessarily for multiple seam designs where underground mining has taken place or that sort of thing. But for the majority of those, it's going to be arms highwall miner, and the main factor for that is going to be the depth, right? Entry or penetration length. Uh, the two main highwall miner systems on the market that I'm aware of have similar penetration depths. Some of those can get up to 1,200 feet, or maybe even 1,500 feet if you're in a really good place and you're doing well with your keeping your hole straight. Um, but generally speaking, a nice, good estimate of how deep you can go is 1,000 feet, right? Entry height, we talked about the main factors determining it, being, the equipment or the coal seam thickness. And then finally it asks, discuss how your chosen parameter might interact with one other parameter. All right, so obviously, if you're talking about web pillar width, then it's easy to say that it would interact with your barrier pillar size, right? And its spacing. Those two things interact, with each other. The mining height or mining depth or penetration length, that in turn, can interact with uh, the other parameters that it might interact with is the extraction sequence, right? So I remember I said, you want to try and get your longer holes in first. But if there are conditions to dictate otherwise, you can start shortening those holes, change your sequence, turn around, come from the other side and maybe get the longer holes back in that way, right? So a lot of times with highwall mining, you do get a second opportunity if things start to go wrong to go back in and get that coal, okay? And then of course, entry height, that also, interacts with the pillar width and the barrier sizing, right? Those three do work together and combine, into what, results you get for your stability factors, for your design. So that pretty much finishes up week 6, which that's one of the more lengthy discussions that we had this semester so far. And probably want to follow up with week 7. And this was stuff from the the West Virginia DEP handbook. And they set numerical limits on certain things like sediment storage has to be 0.125 acre feet per acre disturbed. 3% slope limit on fill drainage surfaces, right? So, like if you were to do, a valley fill, the top of it, right? The top of that fill, they limit the slope of that, right? So you don't get a ton of like runoff that hits it, and it allows us to better control the drainage on those fills. And then finally, a 10% sustained haul road grade. So, which of these standards would be the most difficult to meet in a real world project? It's probably going to be one of two things: the sediment storage capacity. Okay, so a lot of times in steep terrain, it's difficult to get the storage capacity you need. Um, a lot of times you're probably not going to be using ditches for that. You'll probably use a pond that you can put in a nice centralized location. But so that can be kind of difficult at times. And then the steepness of our terrain, okay, can sometimes make the 10% sustained haul road grade difficult to achieve, right? And sometimes that can happen, particularly in regards to the project that we're doing in this class, right? Where you have relatively steep terrain. You're going to be backfilling a bench, on contours, mine. You're going to be backfilling that bench. Sometimes, particularly if it's steep, you can get excess material, right? And you're trying to repack it onto that open contour, and what happens is you end up with more material than will fit there. And if you don't have a storage place for it, what ends up happening is you get material coming off the outslope, right? So you get material coming down. Maybe that goes down to a lower bench on the coal seam. I've seen that happen, right? So that there was so much extra material that we filled in the whole lower bench and then still continued that slope back up to the new bench. Okay, and then what happens is now you can't haul on that bench anymore. You've got to come in around and put in a whole new haul road back up to that pit that's up here, right? So that ends up being a pretty steep stretch of road trying to do that. I've seen it happen. I've seen it not be met in the real world. Um, and in that case, overall, yeah, sure, I'm sure the grade was fine. But that particular section of it was quite steep, um, and that sort of thing. Now, how might exceeding these limits impact safety and stability? Well, I think the stability of that particular road was just fine. What was, impacted the safety of it was that you couldn't see up that road, right? When you started to go up, and you can't see the top. So you'd have to radio, get on the CB and let people know that you're either coming up that portion of the haul road or going down. Um, and so that's what we had to do. We'd have to radio back and forth. But if for some reason somebody didn't hear you, you might be coming up that road, and then all of a sudden here's a 785 haul truck, fully loaded, getting ready to go down, right? And guess what? It's not necessarily wide enough to be able to support that because you've impromptu put this road in, right? You didn't necessarily mean for it to be like this. You meant to just haul around behind the miner. There was too much material. So that's one other, an issue with that might exceed safety or stability. The 3% slope limit on those fill surfaces, um, if those were too steep, right, um, what you could get is excess runoff, which could then, um, you know, erode the face of the field, right? The whole point is that you have these drainage surfaces. They're not that steep. They come to this either growing ditches on the side, a durable field drain in the middle, or maybe even both. And if it's too steep, you potentially too much runoff there that might wash those out, that sort of thing. Mm. And excuse me. And then as far as safety from sediment storage, yeah, I don't really think that impacts safety or stability necessarily in either of these cases, but what you could get, particularly with a relatively extreme rainfall event, is sediment discharging into the creeks. You end up with black water in the creeks, and trust me, you don't want that. People will be calling you. People will be wondering what's up with this. I've seen it happen before. It's not good, and it's not worth it. So it's best to keep your creeks as clean as you can. One, it's just good practice, and two, it helps keep everybody around you in the community happier. Um, What else? How would you measure compliance with a standard in the field? Track progress over time. Okay, so the point of this sort of discussion question was um, basically to try and get you to start thinking about what we call as-built certifications, right? So what we do is we'll come up with a design and a plan, right? This is what our design is, what the plan is. We go out in the field, we build it. A lot of times it meets the plan, right? A lot of times it's fine. But sometimes you get out there and the conditions aren't necessarily what you thought they were, and things are a little bit different. And then you have what's called an as-built certification. So you build it, you survey it. That's probably the key, right? To measure compliance, that you'll be surveying your haul roads, be surveying your sediment control structures, and you'll be surveying your fill structures so that you know what shape they are, what their slopes are, what size they are, how much storage there is, all of those things. You'll be measuring compliance with surveying for the most part. And tracking progress over time, you may do multiple surveys, right? And like I said, these are both for design. You can put grade stakes if you're doing a road. Same if you're doing grades on fills. You'll be putting those in. Then after you're done, you'll get a final answer. This is what it is, um, and that sort of thing. So that's how you're going to measure compliance and make sure you're staying on track over time. And so with that, we've covered 7 weeks, 6 weeks, I guess, um, of discussion posts, and this is for the first half of the semester for the surface mining class. So with that, um, we'll see you next time, and we'll be getting back on to discussing the projects. So we'll see you then.